Let's get that recorded. So today we'll be talking about Lab 7, which is the Empirical Formula Laboratory. So let's first define the empirical formula. So what do I mean when I say empirical formula? So we've actually already seen an example of the empirical formula when we discussed the law of multiple proportions. So the empirical formula is the simplest, oops, one moment, is the simplest ratio of atoms of each element in a compound. So for example, if we looked at N2O4, so N2O4, let me erase that and write that a little bit more clearly. So in N2O4, we have how many oxygen atoms? 4. So we have 4 oxygen atoms. And how many nitrogen atoms do we have? 2. 4 oxygen atoms to 2 nitrogen atoms. So that in turn, this 4:2 ratio can be simplified, right? There's a simpler ratio of atoms of each element. This can simplify to 2 oxygen atoms per every 1 nitrogen atom. So our empirical formula would be NO2. Now, just like we can figure out our empirical formula by looking at the ratio of atoms, we can also figure out the empirical formula by looking at, and this is the alternative way of thinking about the empirical formula, is the simplest whole number. So whole number means no fractions, no decimals. So the simplest whole number ratio of atoms of each element. And let's replace atoms with a concept that we've discussed today. And what's another way of talking about the ratio of elements? We can count groups of atoms as what? What's a method of counting atoms that we've talked about a lot? We did conversions involving this quantity. What was that? Moles. Moles. So the ratio of moles of each element. Okay. So really the empirical formula can be thought of as the simplest whole number ratio of moles. So for example, if we were looking at N2O4, we could set our mole ratio, we would have, and we would expect to see 4 moles of oxygen per every 2 moles of nitrogen, and that would simplify to 2 moles of oxygen per every 1 mole of nitrogen. And that would give us the empirical formula of NO2. Okay. So now that we have the idea of the empirical formula as a mole ratio, what we're going to be doing today is calculating the empirical formula of a range of different compounds by measuring the mass before and after a chemical change. So let's talk about our 3 major cases. So there are 3 major branches and 3 major reactions that we are going to be looking at today. And we're going to use these 3 reactions in order to figure out the empirical formula of each of these 3 different compounds. So in case A, what's one of the first systems we're going to be looking at? What reaction are we going to be looking at? Combination between what 2 species? What 2 elements? Magnesium and oxygen. Okay, so we're going to take magnesium solid, react it with oxygen gas, and we will generate what we think. For right now, I'm going to write this as MgO, and it's your job to figure out whether I've prepared the correct formula in this equation. We're going to figure out the empirical formula of our product. Now, that's our first reaction that we're going to be looking at, and 1/3 of the class will be looking at reaction A. The second third of this class will be looking at reaction B. And what is system B? What chemical system, what chemical reaction are we going to be looking at? Decomposition, yep. And we're going to be decomposing what species? What compound are we going to be decomposing? What was that? What's the exact solid that we'll be decomposing? This is really important. Carbon dioxide is a product. We're on the right track. It's a carbonate decomposition, just as a hint. So let's open up our lab books and let's really try to make sure we understand what's going on here. What was that? Calcium oxide is a product, but what's our starting material? You're very close. What was that? Oh, that's in your pre-lab, but in the actual lab, what species? Yep, that's the first one. We discussed that. So in part, I believe it's part C of your lab text. So carbon dioxide is your product, yes, but what salt are we decomposing? Calcium oxide. What was it? Oxide. That's the product, but what? It's calcium carbonate, CaCO3. This is the tentative, so don't take any of the formulas I write as the exact empirical formula or the exact molecular formula, but we are decomposing calcium carbonate. Upon heating, calcium carbonate will decompose to yield calcium oxide and carbon dioxide, okay? And you have to handle this reaction a little bit differently if you want to figure out the empirical formula, okay? Finally, in case C, what reaction are we looking at in case C? What reaction, what compound are we trying to form? Or what are we reacting? Tin and an oxidizing agent. So I'm going to write this as tin solid. And what is our oxidizing agent in this case? What are we mixing the tin with? Nitric acid. So nitric acid is serving as our oxidizing agent. You can just think of nitric acid as our source of oxygen atoms in this case. And we're going to form tin oxide. And notice how in the way that I've named this compound, I'm ambiguous with respect to the charge of tin. And that's going to be your job to figure out by determining the empirical formula. Okay, so we have all of our reactions established. Let's talk about what we're going to actually do in each of these 3 steps. So in part A, we're going to look at the reaction of magnesium with oxygen. So we're going to take our crucible. And we're going to measure the mass of our dry crucible. So we're going to measure the mass of our dry crucible. We've done that before, right? It needs to be clean and dry, flame dry, just like we did in lab 5. Then we're going to need to place a piece of magnesium ribbon into our crucible, and we're going to measure the mass of magnesium that we've added to our crucible, okay? So we're going to put our little magnesium ribbon into the crucible. So this is our magnesium ribbon. Now, it's really important that we talk about how we're going to heat this magnesium. Should we go all out with a super strong flame initially? No. So you're going, once you've measured the mass of the dry crucible and the mass of the crucible with magnesium, you're going to then take your crucible containing your magnesium strip, and you're going to heat it gently. And the key thing to keep in mind, does our cap need to stay on, oh, one moment. Does our cap need to stay on the crucible? How should we handle the cap? Can I just leave the cap off willy-nilly? No. So you're going to heat gently, and then periodically, you're going to open the crucible to allow oxygen in. So you're going to open the lid periodically, open it slightly, you'll let some oxygen in, and what you're on the lookout for is if you see a white light, you need to put the cap back on. So you do not want to see a light. Do not look at the light. If you observe the light, you're going to need to put the cap back on to restrict the oxygen intake, and you're going to have to restart. You never want to see the magnesium burning and producing light. That's a sign that the combustion is not controlled. Does that make sense? Okay. Eventually, after heating gently, you're going to end up seeing almost a gray powder. So let's change colors for that. You're going to see a gray powder at the bottom of your crucible. So this is your magnesium oxide. So you've successfully reacted the magnesium with oxygen. And as a final test, once you have only the gray solid at the bottom of your crucible, you're going to open the crucible top. And then you're going to heat for approximately 30 seconds. If you see any shiny metallic magnesium ribbon still remaining, do not open the top all the way during heating, or you will see a bright light and you'll have to start from scratch. Finally, considering we now have a crucible filled with magnesium oxide, we can complete this experiment by measuring the mass of magnesium oxide. Does that make sense to everyone on what you're doing? Okay. Now, how do we use all of this data? How do we use all of this data? Well, in the end, in order to figure out the empirical formula, we need the moles of magnesium per moles of oxygen. Okay? So our first order of business is we're going to take the grams of magnesium and convert it into moles of magnesium. We can do a mass to mole conversion, right? We've done that before, right? Okay. The second step is we need to figure out the grams of oxygen. And it's important now that we draw a picture. So we have magnesium reacting with oxygen to give us magnesium oxide. So if we know the mass of magnesium, so we know this mass of magnesium, and we know the mass of the magnesium oxide, would we expect our mass to increase? If we react with oxygen, if we compare these two formulas, would you expect magnesium oxide to have a larger mass? Yes, right? It has an extra oxygen atom in its formula. So where did that mass come from? Where did our increase in mass come from? What was incorporated in this reaction? Oxygen, right? So then, by conservation of mass, the final mass of our magnesium oxide is going to be equal to the mass of magnesium plus the mass of what? Oxygen. Plus, and I'm going to write this as the mass of just normal atomic oxygen, since all the mass of oxygen incorporated in our product came from oxygen in our air. Okay? So then, we can solve for the grams of oxygen by taking the mass of magnesium oxide minus the mass of magnesium. And then finally, we can go from the grams of oxygen to the moles of oxygen. Is everyone comfortable accomplishing these three steps? Okay. Okay, so that's the first part A. So I'll be able to let loose a third of you on part A. Let's talk next about part B, just for completeness. So for part B, we're looking at the decomposition of calcium carbonate. Okay? So just like before, you're going to have your empty crucible. You're going to have your empty crucible with the cap on. So you're going to measure the mass of the crucible. Okay? We can do that, right? Make sure the crucible is clean and dry. Next, you're going to put in a mass of calcium carbonate. And how much calcium carbonate did they tell you to put in? About. Just approximate here. Let's make sure we're not loading it with too much or too little. How much does it say in the lab manual? About 1 gram. Okay, good. So you want to shoot for around 1 gram. So notice this is 1 sig fig. So as long as you're within 0.9 to 1.1 grams, you're good to go. Don't obsess with getting it exactly on the dot, just order of magnitude, same region. Okay, so we've loaded up our crucible with some calcium carbonate, okay? Perfect, perfect. So far, so good. Next, we are going to heat our crucible. And this is really important because this is how people end up accidentally breaking glassware. Here, do I keep my lid slightly open or fully closed for the calcium carbonate? Yeah, so you're going to heat with a open lid. So you're going to heat with an open lid. The reason being, if we look at this decomposition, carbon dioxide, is that a solid, liquid, or a gas? It's a gas. And you're going to need to use a relatively strong flame towards the end of your heating to get this reaction to occur. But you're going to start with a gentle flame and increase the strength. So you're going to heat with the open lid because escaping from your crucible is carbon dioxide gas. Okay? If you heat it with the lid closed, you're going to build up pressure, the lid's going to pop off, the cap's going to break, it's going to be a disaster. Does that make sense? Okay. So at the end of our heating process, you're going to want to do one last strong heating to complete the reaction. And at the end of this entire process, you're going to end up with a crucible. I'm drawing it open just to emphasize it should always be open. And inside the crucible will not be calcium carbonate, but calcium oxide. Okay? Carbonates decompose to yield an oxide and carbon dioxide. So now, what we're going to do is we're going to highlight the steps involved in this calculation. So first and foremost, to figure out the empirical formula, this is where we're going to need to get a little bit creative. You're going to look at the mole ratio of calcium oxide per mole of carbon dioxide. And you can figure out how many atoms of each of these units are in our starting material by looking at this mole to mole ratio. Does that make sense? So for example, if we had 1 mole of calcium oxide per 1 mole of CO2, that would tell us we have 1 calcium, 1 carbon, and 3 oxygens. So this is a little bit different than your traditional empirical formula calculation. Does that make sense to everyone? What ratio you're calculating? Okay, so let me show you how to calculate this. So first and foremost, we're going to need to go from the grams of calcium oxide to the moles of calcium oxide. Can we do that? Can we do a mass to mole conversion given a molecular weight? Yes. In the second step, we're going to need to figure out the grams of carbon dioxide. And just like before, we're going to draw a bit of a picture here. So if our calcium carbonate is decomposing to yield CO2 and calcium oxide, and if we know the mass of calcium carbonate and we know the mass of calcium oxide by conservation of mass, is our if as we heat the solid, what's going to happen to the mass of solid in the crucible, the mass of just solid? Will it increase or decrease? Looking just at our formulas and their molar masses. So we go from calcium carbonate to calcium oxide, so let me phrase this another way. Does calcium carbonate have more atoms than more atoms of each element than calcium oxide? Yes. So then we'd expect calcium carbonate to have a larger molar mass, right? So if looking at this mole ratio is 1:1. So if we're heating this calcium carbonate and we're losing some atoms, we're losing a molecule of carbon dioxide that's just floating off into our environment, will we lose mass as a result? Yes. And based on conservation of mass, what is the entirety of our mass lost? Yes, in the carbon dioxide, exactly. So the mass lost during heating is the mass of carbon dioxide present. So then we can figure out the grams of carbon dioxide by taking the mass of calcium carbonate minus the mass of calcium oxide. Does that make sense? And we can do that, right? We can subtract these two masses. Finally, in order to complete and get our moles, we're going to need to go from grams of CO2 to moles of CO2. And we can do that, right? Can we go from grams to moles given the molecular mass? Yep, we've done that before. Does that procedure make sense to everyone on how to solve this and perform these calculations? Okay, let's do one more. So the last case that we're going to be doing is the tin and nitric acid. So just like before, you're always going to need a clean, dry crucible. So we're going to measure the mass of the crucible. And into this crucible, we're going to put some tin. Now be really careful when handling tin. And about how much tin are we going to put into this crucible? 0.5, yep. Now, do not breathe in the tin. Avoid contact of the tin directly with your extremities. Tin is quite toxic. Okay, next, in the fume hood. So in an operating fume hood. So you're going to need to bring it over there and turn on the fume hood, okay? And if you need assistance in operating the fume hood, I'll be assisting you throughout this process. You're going to need to make sure it's on. You'll hear the sound of it operating. You'll hear a visible sound of air movement. So in the operating fume hood, you're going to take your crucible containing tin, and what are we going to add to that tin? Nitric acid, HNO3. And about how much nitric acid, according to the procedure, are we going to be adding? How much? About six drops. Is that the exact amount that we need? Any more recommended? Just to make sure, you really want to be careful with this, that you're not adding too much nitric acid. So you want just enough so the solid appears clumpy and that it's well mixed, okay? I don't want to see a layer of liquid. That's way too much. If you have too much nitric acid, it's going to be a pain to boil it off. Okay, so once that is established, once you have that established, looking at our procedure, we are going to take our sample, we're going to have our lid partially open, and we're going to gently heat our tin and nitric acid. You're going to gently heat with the cap off. This is why I don't want to see puddles of nitric acid. If you have too much, you've made a mistake. Just add the minimal amount, 6 drops, exactly as required. Okay, finally, at the end of gentle heating, you'll be left in your crucible with a sample that is no longer just tin, but a sample of tin oxide. So we can record the mass of tin oxide, right? So then, just like we did in our magnesium example, in order to figure out the empirical formula, we're going to need a mole ratio of the moles of tin per mole of oxygen. Okay? So to accomplish that, first and foremost, we're going to need to convert the grams of tin into the moles of tin. And we can do that, right? Yeah. The next step, just like we did in the magnesium example, so thinking about this, we have tin reacting with a quote-unquote oxygen source to make tin oxide. So if we know the mass of tin and we know the mass of tin oxide, can we figure out by a difference the mass of oxygen? Yeah, by conservation of mass we can. So then we know that the mass of oxygen is equal to the mass of tin oxide minus the mass of tin. And then finally, we can go from the mass of oxygen to the moles of oxygen, right? Mass to moles using the molar mass. That's pretty well established. If you need any help with that, I'm more than willing to help walk you through the calculations on your exact data set. So now that we're clear on what we're doing today and how we're analyzing our data, again, I cannot stress enough, nitric acid must be done in the hood. The heating step, once the reaction is complete, can be done outside of the hood, but you should use the minimal amount of nitric acid possible. If you see yellow smoke, you need to cut the flame immediately, as that's a sign you're generating noxious byproducts. Okay, and just as a reminder, the steel wool is only needed for the magnesium. So what I'm going to do is each group will come up. I will assign a group A, B, or C, one of these three reactions. You'll only be responsible for that reaction. You'll be doing 2 trials and you can do them at the same time. So while one crucible is cooling, you'll run the second crucible under a heating step. Does that make sense? There are more than enough crucibles on the side. If there are no other questions, please come up and I'll assign each group a reaction. And please put your goggles on and you're welcome to begin.